Theorem 19. Theorem 19 states that the angle subtended by an arc at the centre of a circle is equal to twice the angle subtended by the arc at any point on the remaining part of the circumference. Suppose we are given a circle, centre O, with an arc DSE of the circle, and any point T on the remaining part of the circle. There are two cases to consider. Figure 1 shows the arc DSE as a minor arc with angle DOE subtended at the centre, and angle DTE subtended at the circumference. Figure 2 shows the arc DSE as a major arc with the reflex angle DOE subtended at the centre, and angle DTE subtended at the circumference. These two figures illustrate case 1. If point T on the circle is close to one end of the endpoints of the arc, we get a different diagram. Look at figure 3. Point T on the circle is much closer to the endpoint E of the arc DSE. You can see clearly from this diagram that the situation is rather different from the situation in figure 1. This figure illustrates case 2. However, we must prove that no matter which case arises, angle DOE is twice angle DTE. Once again, in order to prove this theorem, we must make a construction. In each figure, we join T to O and extend the line to R to form the angles O1 and O2. If you look carefully at each diagram, you will see why we do this. In each case, TOR forms two isosceles triangles, each with an exterior angle. This enables us to use the isosceles triangle and the exterior angle of a triangle theorem. Look at the proof. In all of the cases, angle D1 is equal to angle T1, since the radii DO and TO are equal, implying that the triangle TDO is isosceles. But angle O1 is equal to angle T1 plus angle D1, because the exterior angle of a triangle is equal to the sum of the interior opposite angles. We hope that you remember this theorem. Similarly, angle O2 is equal to twice angle E1. This part of the proof applies to both case 1 and case 2. But from now on, we must consider each case separately. For case 1, consider figures 1 and 2. Angle E1 equals angle T2, since triangle TOE is isosceles. The radii TO and OE are equal in length. Therefore, angle O2 equals twice T2, since we have already proved that O2 is equal to twice E1. Thus, angle DOE, which is equal to angle O1 plus angle O2, is equal to twice T1 plus twice T2. Since we have proved that O1 is twice T1 and O2 is twice T2, angle DOE must be equal to twice angle T1 plus angle T2, which is twice angle DTE. Thus we have proved in case 1 that the angle subtended at the centre is twice the angle subtended at T on the remaining part of the circumference.